Hi, I'm Sanjari from KAIST, and I am very happy to present our work, Fluid XP. This work has been done in collaboration with KAIST, Digest, Aju University, and Simon Fraser University. One of the major trends in mobile computing is the enrichment of mobile multi-device environment. From smartwatch to smart TV, mobile devices have various form factors, and their operating systems are becoming increasingly diverse. With such a trend, many techniques have been introduced to enable multi-device interaction. For instance, Chromecast allows specialized apps to cast video to external display devices. Apple's Sidecar and Android's secondary display allows users to use mobile devices as an external display. And screen mirroring techniques allows users to control their mobile devices with secondary devices. On top of existing techniques, a recent work, Fluid, has presented a groundbreaking multi-device interaction framework. Fluid provides unique and outstanding multi-device interaction experience by allowing unmodified off-the-shelf mobile apps to distribute its individual UI elements to other devices in a flexible, transparent, and responsive manner. However, one limitation of Fluid is that it does not have cross-platform support. Because of Fluid's fundamental design that bases on object serialization and remote procedure call, Fluid only supports UI distribution between Android devices. Such limitation is very critical in terms of applicability, since modern-day multi-device environment is oftentimes platform heterogeneous, where different device types typically have different major platforms. So, to overcome the limitation of Fluid, we present Fluid XP, a mobile platform that can distribute UI elements to different devices, not only in a flexible, transparent, and responsive manner, but also with cross-platform support. Let me show you an example. In this scenario, a user is watching a live streaming app through TV. Oftentimes, the user might want to chat with other users. However, when user clicks the chat UI, the keyboard overlaps the screen and makes the video very small, making it very inconvenient to chat and watch video at the same time. In such case, user can use Fluid XP to distribute chat UI from TV to his smartphone to watch video in full screen while chatting with his smartphone. Our key idea is UI tree partitioning and sub-tree streaming. Basically, UI tree is the representation of how app is going to be rendered on the screen. Through a sequence of rendering processes, UI tree is translated into a collection of pixel data and displayed on the display. We extend such inner behavior to multi-device environment by partitioning and streaming them. Let me explain in more detail. First, when user selects UIs to distribute, Fluid XP separates the selected UIs from its original UI tree and creates a subtree consisting of selected UIs. Then, we render the partitioned subtree on an invisible display called virtual display, and stream the pixel data of the virtual display to the guest device's Fluid XP wrapper app. Note that we use pixel data as a medium for UI distribution, since pixel is a universal, platform-independent data format used in all display devices. Now I will introduce three main problems in realizing such key idea and discuss their solutions briefly. The first problem is how to partition the UI tree in a way that it does not contaminate the integrity of the app's original behavior. Because app logic is tightly coupled with the structure of the UI tree, it is very dangerous to arbitrarily partition the UI tree without modifying the app's code. For instance, in this case, when the app logic requests UI tree to return the second child of a UI A, the original behavior of the UI tree would be to return the UI C. However, if the UI tree is naively partitioned like this, the UI tree will return index out of bound exception since UIA no longer has second child. Therefore, our solution to this problem is single UI tree illusion. Specifically, we give app logic an illusion that UI tree is singleton even after it has been partitioned. We do so by creating a virtual link between the original UI tree and the UI subtree and give app logic access to the partitioned subtree. With such illusion, we can preserve the app logic's behavior toward the UI tree. Consequently, our partitioned mechanism offers app logic and rendering process a different view on the UI tree. From the perspective of app logic, UI tree remains singleton so that app logic can preserve its app behavior, while from the perspective of the rendering process, UI tree is partitioned into two different subtrees so that each tree can be rendered on a different display. Our second problem is how to stream the UIs with minimum network transfer. For resource efficiency and high quality streaming, FluidXP minimizes the network usage. To this end, FluidXP aims to transmit only minimum pixel data required to compose the display, which is the delta pixels between two consecutive display frames. However, in modern mobile platforms, UI rendering is done in an integrated manner. In other words, visual change in any one of the UIs in the display triggers the whole display pixels to be re-rendered, making it difficult and time-consuming to find the delta pixels. Our solution is per UI rendering and streaming. To do so, we further break down the UI subtree into multiple root trees, each composed of leaf node UIs. Then, we render each root trees on a separate virtual displays and stream them to the guest device through independent channels and compose them from the guest side. Such isolated rendering and streaming mechanism allows FluidXP to automatically render and stream only the UI with visual change. In other words, FluidXP can transmit delta pixels without any additional computational overhead. The third problem is how to choose which streaming protocol to use. In streaming, the streaming quality heavily depends on the streaming protocol, and choosing the optimal protocol based on the characteristics of the UI is very important. However, in many cases, different UIs have different characteristics and they often conflict with each other. For instance, a video UI is loss tolerant but delay sensitive, whereas text UI is loss sensitive but delay tolerant. As such, there is no one-size-fits-all protocol that can satisfy all UI characteristics. Therefore, our solution is per UI optimized protocol. Recalling that FluidXP streams each UI elements through isolated streaming channel, we allow UIs to use its own optimized protocol based on its characteristics. Note that any streaming protocol can be a candidate, including network protocols such as RTP, HLS, and any other state-of-art streaming or even UI distribution techniques. For more technical details, please refer to our paper. For evaluation, we implemented FluidXP host prototype based on Android version 10 and developed guest wrapper app for Android, iOS, and Ubuntu platforms. We performed evaluation using a combination of 4 different devices. First, we evaluated the functional coverage of FluidXP using 19 mobile apps from Google Play Store and 1 custom-made app. We have come up with 11 new multi-device use case scenarios and have confirmed that FluidXP successfully supports all 20 off-the-shelf mobile apps. Also, we measured the network usage of FluidXP and compared it with other multi-device streaming techniques. As a result, we have confirmed that FluidXP consumes up to 69% less network usage under the same streaming environment. Furthermore, we evaluated the overall streaming quality of FluidXP and compared it with other streaming techniques. This is a video demonstration of FluidXP compared with TCP and UDP version of screen copy. As you can see, TCP version of screen copy inflates delay in the video, and the UDP version of the screen copy inflates visual degradation. On the other hand, FluidXP shows none of such drawbacks. For detailed quantitative results and interpretation of the evaluation, please refer to our paper. And finally, we conducted a user study on 25 participants and asked them to evaluate the usability of the FluidXP. From the study, we found that most participants felt FluidXP satisfying in both performance and use case perspective. Also, we found that users have diverse opinion on which app is the most or least useful. This confirms that FluidXP's flexibility in allowing users to choose which UI to distribute can serve big advantage in the real world. And in conclusion, we designed and implemented FluidXP, a mobile platform that enables UI distribution across heterogeneous platform devices via UI tree partitioning and substrate streaming. We evaluated our system with 20 off-the-shelf mobile apps through both quantitative and qualitative measures. Lastly, we expect FluidXP to accelerate the development of novel apps that advance multi-device user experience to the next level. Thank you for listening.